Right, this is the second video for chapter 26, covering pages 499 to 503. So you may have noticed that out there in the world, there are materials that when light shines on it, the light goes through it. And there are materials that when the light shines on it, it doesn't go through it. So your table would be an example of an opaque item. And transparent materials, we think of things like some plastics are slightly transparent, glass is transparent. So what makes it whether or not something is transparent or opaque? So when the light is transmitted through the matter, then some of the electrons are forced into vibration, right? And so the way that the material responds to the light is going to depend on the frequency of the light coming through and the natural frequency of the material. So things that we think of as transparent, all we think of it as being transparent to, all it really is transparent to necessarily is white light that we can see, visible light. That doesn't mean it's transparent to other types of light or radio or electromagnetic waves. So if the light passes through without causing huge vibrations, then the light will come out the other side and be re-emitted. If the light hits it and causes high amplitude vibrations, lots and lots of vibrations, then it will either be trapped inside or it will bounce off, and then it is not re-emitted. So if it is re-emitted, then it is transparent. Things that are opaque absorb the light without re-emitting it. So the table, the book, our clothing, people themselves, light is absorbed without re-emitting it. So in order for you to become invisible and become transparent, you would have to figure out how to take visible light and let it pass through you without being absorbed or causing high vibrations within your own electrons. Now, the vibrations of the atoms and molecules are turned into kinetic energy or internal energy. So if you've ever noticed, when you're sitting out in the sunlight is hitting you, it is not passing through, it is being absorbed. We get warmer. That warmth is the vibrations of the atoms and molecules within our bodies that are kinetic energy or internal energy. Or if you've ever felt an object that's been sitting outside, it is collecting that energy as well, and so it is going to get warmer. Glass, if you're going out to your car at the end of a hot day and you touch the glass on your car is not going to be hot because it's re-emitting the light. But if you touch the surface, the metal, that can be hot because some of that energy is being absorbed and turned into internal energy. Now, if it's an opaque item, then the vibrations of the electrons inside are going to be at high amplitudes, which means lots and lots of vibrations, so the light can't come through. Metals are opaque, but they're slightly different. What happens is that when a light hits a metal object, the electrons that are kind of free or loose on the edges, remember metals are good conductors because those outer shell electrons can get bumped free very easily. So the light, when it hits these electrons, it just sends the free electrons into vibrations, and instead of the vibrations bouncing from atom to atom, they just reflect off. So that's why metals appear shiny, is because the light is being reflected off of the vibrations of the atoms rather than being absorbed. So when light hits something that is not a shiny object, it is absorbing it and it's causing the vibrations, but they stay inside the object instead of bouncing back off. Now, whether or not something is going to be transparent or opaque, like I said, depends on the frequency of the light and the frequency of the object. So if those are equal, if the light is equal to the electrons of the material, it's going to be opaque. So you can assume that when visible light is hitting your table, that the frequency of that light is probably equal to the frequency of the electrons in the table, because the light does not bounce off because it's not shiny, and it doesn't pass through. So in order for it to be transparent, they cannot be equal. If they're equal, it's going to be opaque. Now, if it's just less than the frequency of the electron, so the light shining on it is a little less than the electron frequency of the thing, it's going to be transparent. So we can assume that glass, because it is transparent to visible light, that the frequency of the glass is slightly more than the frequency of the light, and that is why it can pass through. If it is a lot less than the frequency of the electrons, then it will also be opaque. So in order for it to be transparent, the frequency of the light has to be just a little bit less than the frequency of the electrons. They can't be equal, it has to be a little bit less. And then there are some things that are semi-transparent, which just means some of it will get through. Remember I said plastic is sort of transparent. We would say it's semi-transparent. Some of the light gets through, but not all of it. So let's talk about transparency of glass. So the natural frequency of glass is equal to ultraviolet light. So if you've got sunlight from the sky shining down into your window, the natural frequency of that glass is going to match the natural frequency of the ultraviolet light, but not of the white light. So that's why visible light comes through, is because the glass has a different frequency. So the ultraviolet light, since it's the same frequency, is going to be opaque. And that is because the energy from the ultraviolet light is actually getting trapped, because it makes the atoms vibrate so much that it gets trapped and it can't come through. Now remember, ultraviolet light is what causes sunburns on our skin. So you will never get a sunburn through glass. So sitting in the car with your, sitting in the car driving around, you're never going to get a sunburn through the glass in your car. You'll get a sunburn if you roll down the window and stick your arm out. You can get a sunburn on your arm, but you'll never get a sunburn inside your car, because it traps the ultraviolet light. Now, one of the things that reptiles, they say that they need is UVA and UVB light. They need some ultraviolet light. It's good for their skin. It's good, healthy for them. The problem with that is that if you just assume that you're putting your reptile tank near a window, that they're getting some of that UVA and UVB light, they are not, because if it's coming through glass, like the glass of the aquarium or the glass of the window, it blocks that out, and so they're not actually getting any UVA or UVB, but you can create a lot of algae growth, because the algae responds to the sunlight as well. So a lot of times they'll have special lights that you have to buy that are UVA, UVB lights, and the glass frequency that they use is not equivalent to UV, and so then it is allowed to go through. Now, for glass, it is transparent to visible light because the vibrations pass easily and they're emitted on the other side. Infrared light, which is going to be slightly lower frequency than visible light, is too low of a frequency, and so glass is opaque to infrared light. It just gets trapped in there, but it causes quite a bit of an increase in internal energy. Some of the energy is transmitted to the other side of the glass. That is part of what causes the heat to rise inside greenhouse, or that's what makes the hot air inside your car, if you're not blocking out your windows to block out that infrared light that's coming through, that causes the increase in temperature inside your car on a hot day. The atmosphere, we can look at the atmosphere and say, okay, it is transparent. You can't see the air, you can't see any of that, you can see clouds, but how does that affect, how is that related to all of the waves that are out there? So the atmosphere is semi-transparent to ultraviolet light. So a lot of ultraviolet light comes through, but not all of it. So that is why you can get sunburned. The sunburn, the ultraviolet light obviously has to get through. What our atmosphere does do is filter out the highest frequency ultraviolet waves, the ones that are even more dangerous. The only ones that get through are the low frequency ultraviolet waves. It's a good thing the big ones don't get through, because that would be very, very bad for us. Clouds are semi-transparent to ultraviolet light. You can get sunburned on a cloudy day. You may not notice you're getting sunburned, but you can get sunburned. Now, the atmosphere is completely transparent to visible light. God created that way on purpose. The whole reason why the sun is out there is to give us light and for us to get energy from the sun. And if our atmosphere was opaque to visible light, then there would be no point in having a sun out there, because we wouldn't get anything from it. So the visible light is able to pass through very easily in the atmosphere. Infrared light, it is semi-transparent. So some of the infrared waves come through, some of them don't. What keeps us nice and warm and toasty on our planet, besides the greenhouse gases? The greenhouse gases, what they do is the infrared light that does come into the atmosphere gets trapped in here. And then the Earth also emits slight infrared frequencies, and those get trapped inside the greenhouse gases, and that keeps us nice and toasty. Otherwise, the planet Earth would be quite chilly. But mainly our atmosphere was designed by God to allow visible light to get through. So when light is transmitted, remember we talked about how fast light has to travel, and it has to travel that specific speed. If it's not traveling that speed, eventually it would die out. If it goes faster, you are disobeying the law of conservation of energy. But they are traveling at 300,000 kilometers per second. Now, when it's passing through a material, it will slow down slightly as it passes through. But if you picture that material, and if we could magnify that, there are lots of blank spaces in between the atoms in a piece of glass, or between the molecules of water. And as it's passing through the void between them, it's going to keep going the same. It's going to speed back up to 300,000 kilometers per second. And then when it comes out the other side, it's going to speed up. So it might slow down as it's passing through, but it will return to its original speed when it's not being hindered by the object any longer. So in a vacuum is where it's fastest. That's at 300,000 kilometers per second. We're just going to call that c as the speed of light. You may recognize that from E equals mc squared. That c is the speed of light. In the atmosphere, it travels only slightly slower than it would in a vacuum. So we would still basically consider that to be c. In water, it goes about 75% of its original speed. In glass, it slows down to about 65% of its original speed. And in a diamond, it's going to slow down to 41% of its original speed. So, but once again, once it passes through, and in the voids in between the molecules inside there, it is going 300,000 kilometers per second. There's a quiz today. Go ahead and click on the link. Take the quiz. Have a good night. I'll see you in class.